Hey guys, welcome back to 6.4, and this is 6.4 part 2. This is like the second part of 6.4. In 6.4, initially we just learned that Q equals mc delta T. Now we're going to talk about thermal energy transfer in terms of actually how we'll use it in class most of the time. What we're going to use is kind of a variation or addition to the formula that we saw before, which is Q of the system is equal to negative Q of the surroundings. Basically what that means is heat lost by the system has to be gained by the surroundings. To kind of look at that as a conceptual example and also to help us with our example below, let's say we have a piece of rock or a hot rock that we've heated up to a certain temperature. We're going to drop it into room temperature water. So the temperature of the water is going to go up because it's absorbing the heat that is being lost by the hot rock. And its temperature will go down. And eventually we'll get to what is called a thermal equilibrium. And a thermal equilibrium is where the temperatures are the same. Temperatures of two substances have become the same. And this is actually the most valuable part of using Q equals mc delta T in practice. So let's look at a practice example right here. We have 32 grams of aluminum, and its initial temp is 45.8 degrees C. It's submerged in 105.3 grams of water at 15.4. What's our final temp is what we're looking for at thermal equilibrium. There's that word again. And we're assuming that the aluminum and water are thermal isolated from everything else, which means there's no heat lost or gained to the other surroundings. So basically what we have here is Q of the aluminum is going to equal negative Q of our H2O, because what is lost by aluminum is gained by water. And so we can just plug in our numbers here. We've got 32.5 grams, because remember, this Q is equal to mc delta T. Our mass of aluminum is 32.5. In our table, we have 0.903 is the specific heat of aluminum, and then we're going to multiply that by the temperature change of aluminum. And there's a couple of ways to do this. The example in the book doesn't do it this way, but we know T final is going to be minus our initial temp, 45.8. And that's going to equal the same thing on the other side of water, but we're going to put all of that in parentheses. And so we've got 105.3 grams. Hopefully we remember by now the specific heat of water is 4.184. And then we're going to do the same thing with our temperature change. We've got T final minus 15.4. And so basically it comes down to solving, and this has maybe been a while since we've done this, but when you solve a type of problem like this, you take these three numbers times each other. So we're going to get 32.5 times 0.903, and that'll be our TF on this side, minus, and then the next case, we're going to take 45 times 0.093, and times 32.5. And so that's what exactly is going to happen on both sides here. And in the end, what we should come out with our final temperature, when we do all of our calculation, should come out to be 17.3 degrees C. So hopefully we understand that and kind of get a little more of basically what we were solving here is thermal equilibrium.